maybe I will stand here. Okay, thank you for the introduction. I will tell you about the influence of pretension on the fatigue durability of rubber with single reinforcement layer. It's a common part of a common project with Slovenia University, so we have also co-authors from there. Oh, yeah.
Arrow down.
Down?
Okay.
Okay, thank you. Okay, so as I told before, it's part of the common project in which we are analyzing fatigue tests, of course, to get information on the degradation of the material. We also try to be as close to a real situation, because it's always good to have some idea in the industry where it could be used. And of course, it's worth analyzing how this pre-strain affects our material. I don't know, it doesn't listen to me. I put it down, but nothing happens. Could you please help me? Okay, thank you. So the aim and scope of this presentation is first to investigate the fatigue behavior of rubber, first with single nylon cord. Nylon cords, well, I will show you a picture how it looks like, what it looks like, but it's like in composites. In classic composites, we would have 0.19 fibers arranged, but here we have cords instead of fibers. In my presentation, I will tell you, I will verify whether and which fatigue characteristics can be used, and analyze if the pre-strain affects and if in which way it affects the experimental results. We conducted double-sided cyclic bending, which resulted in almost pure tension. I know that during bending we have the tensed part and the compressed part, but because of the project of the test stand, it resulted in almost pure tension. I will justify it later. We analyzed different frequencies of bending from 0.5 up to 3.5 hertz. And we also changed the amplitude from 13 to 28 to obtain the diversity of results. Yeah, so here, well, can I show it? Yeah, here you can see a microstructure of the cords. So it's like a lot of long fibers. They're just like a string put together. On next figures, you can see the X-ray of this material. So the arrangement of fibers is 0 here and 90 here. The thickness of the whole structure is 3 millimeters. So here we have 3 millimeters. And in the middle here, we have a reinforcing layer. As I told you before, it's very similar to composites, like classic composites reinforced with continuous fibers. So it behaved really very similar to it. But we had one issue, because in the literature, you can see everywhere that when it comes to fatigue of rubber, the materials start to heat up. And because of it, there appear some problems. So this is why we analyze different frequencies to check how exactly our material behaves in this situation. Okay. So I told you about the test stand, which resulted in almost pure tension, because rubber is very elastic, so we can put a lot of strain in it, and it would just slip out if we didn't fix it here. So we fixed the material here with a piece of metal, and here. So when our actuator was moving up and down, the material couldn't move. So this is why we didn't have a classic bending, meaning the tensed part and compressed part. We had almost pure tension in this part. Of course, we had some bending here in the supports and in the actuator, but it's like it will be the topic of further studies. We also had a tensioner in here. So when the specimen was fixed in these supports, in some specimens we analyzed just this situation, and in other situation we put extra tension with more or less 10%. Of course, then we analyzed the exact value, but it was like from 9 up to 11, so let's call it 10. Yeah, now I will show you the machine in operation, how the test stand works, so that you can understand it a little bit better. Here we have very small amplitude and very small frequency, but I think during this film you can understand, and it will justify why we had almost pure tension in our specimens. Okay, now it will be a little more interesting movie with larger amplitude and with higher frequency. So yeah, now you can see how it worked when it was supposed to work faster. So as I told you before, we expected to obtain shorter fatigue life due to the heating and the rubber, so the molecular chain changes. So everything could happen on the interface especially, but also in the rubber. But our observation was kind of surprising, even though in the literature everywhere we found that the fatigue life should decrease. It didn't change anything actually. So we did tests in lower amplitude, lower frequencies and higher frequencies, and the values of results were very similar. The main difference was the shape of the hysteresis loop. When it was slow, the hysteresis loop was very smooth, but when we started to make a higher frequency, the hysteresis loop was very sharp, let's call it. Okay, we had some issues analyzing the fatigue life, because the first thing is how to define when the material cracks, because it's not so obvious. So we couldn't see the real cracks sometimes. Sometimes we did. Sometimes we found just cracking of the material, but sometimes no. So we were looking for a good solution. And the best one for these materials especially was 50% force drop. When we found that the force dropped to 50%, we knew that the material failed. But it's not so obvious, because we also, and now I'm telling you about the 0-90 situation. But for the plus minus 45 degrees, more interesting things were happening, because, of course, some specimens behaved like 0-90. But in the case of the same specimen with pre-strain, 10% pre-strain, this graph isn't so obvious. And also when the amplitude was low, like here we had 22 millimeters, it's not very low, but in comparison with 25, it's lower. The shape of the diagram looked like this. And even we didn't obtain the 50% force drop, but well, I saw the specimen and it was totally failed. So in case of our 0-90 specimen, of course, we can use the 50% force drop, but I wouldn't call it a universal solution. We have some issues concerning this thing. Okay, so about the strain distribution in the material, we used some DIC. Theoretically, there is no use in DIC because we had displacement control, but actually, it appeared that, first of all, it confirmed that we had also almost pure tension, because nothing almost was in blue. Yeah, so we can see that it was tense. But also very interesting things were happening here. What happens here in this yellow places, where there were fibers. So the rubber was stretched and the cords weren't. So this is why we had very interesting things in the middle parts in points. We are analyzing it further right now. It's not really the topic of this presentation, like strictly, but I think it's so interesting. I thought it was so interesting that I decided to show you that very interesting things happen in the material. Okay, so now moving on to the fatigue characteristics. we had two ideas. Well, the first one was to take the amplitude, the strain range. I will tell you what's happening here, because the actuator moves like this. It's up and down, up and down, up and down. But what happens in the material? It's when the actuator goes up, of course, the material is stretched and then comes to zero. But then the actuator goes down and the specimen is tensed again. So it's more or less like this. It comes like this shape all the time. So we thought it would be a good idea to put this epsilon range, the strain range, as for the fatigue characteristics. But another solution was, in this case, epsilon max is the same as the epsilon, delta epsilon. But with it's I mean, okay, maybe different. Here we have the strain range, and with 10% pre-strain, the delta epsilon is the same as here. But we also have epsilon max, which is maximum strain, which is the same in the case of no pre-strain. But when we have pre-strain, it's a little bit higher because it's like this extra 10%. So we prepared two fatigue characteristics. The first one was with the strain range, and it showed that the points were like anywhere. No rule was found here. But when we analyze the maximum strain versus number of cycles to failure, the shape of the fatigue characteristics according to Baskin was really good, and we could identify the fatigue characteristics. So it's a really good solution, and it found out that this maximum strain versus number of cycles to failure is a good solution. So summing up, fatigue life is first, like the most important is that the fatigue life is well described by this maximum strain cycles to failure characteristics. And the relationship is universal. It doesn't matter if we had pre-strain or not, it just gave us the a little bit of mean stress effect. Yeah, the pre-strain increased the variability. It's consistent with general rules, and it's good to analyze it for the real life material. And thank you for the attention.